Okay, let's look into chapter 6, which has to do with thermochemistry and heats of reactions. Okay, thermodynamics, sort of thermochemistry too, thermodynamics is a little more broad, is the science of relationships between heat and other forms of energy. Okay, so thermochemistry then is the study of the quantity of heat absorbed or evolved by chemical reactions. So we're going to look especially at changes of heat. But to do that, let's start out just by talking about energy. Okay, energy is just defined as the capacity to move matter. I'm sure you know all the different kinds of energy that there are. There's, radiant energy from the sun, which is also electromagnetic radiation, or energy from lights, X-rays, things like that. There's thermal energy, which is associated with the motion of a molecule. And there's chemical energy, energy stored within the structure. There's also, some other kinds of different energy. Electrical energy, which is sort of related, has to do with electrons. There's mechanical energy, which has to do with movement in general. Lots of different types of energy. The law of conservation of energy says that energy cannot be created or destroyed. So it can change from one type to another. It just can't be created or destroyed. So you've probably heard there's three broad types of energy. Well, you've probably heard of two of these three broad types of energy. The first one is called kinetic energy, which is just generally the energy having to do with motion. So if something's moving, it has kinetic energy. Potential energy, which is generally considered stored energy, or the energy of an object by virtue of its position in a field of force. So gravity being one of them. We all have, if we raise a book up high, it gains potential energy because you're pulling it against gravity. So gravity is a type of field of force. And then a third kind of energy that we're going to talk about is internal energy. And it's really kinetic energy and potential energy of the tiny molecules and particles making up a substance. So when we're talking about a chemical reaction, we want to know what's actually happening inside the reaction to the molecules. So that's the internal energy. All right, let's just talk real briefly about kinetic energy. Kinetic energy has the equation 1/2 mv squared. So kinetic energy is directly related both to mass and velocity. V is velocity. So this is kind of something you've already thought about, I'm sure. If you've got a car moving at 90 miles per hour or one going at 15 miles per hour, the one going at 90 miles per hour has a greater kinetic energy than the slower one. So if they're the same size, so if mass is constant, one going faster has more energy than the one going slower. In a similar way, if we have two vehicles going at the same speed, so like a semi-trailer or a Mini Cooper, then if they're going at the same speed, they have the same velocity, then clearly the bigger semi-trailer has more energy because of its mass than a tiny little car. The unit that we're generally going to use for energy is joules. We could use joules or we could use kilojoules, where there are 1,000 joules in 1 kilojoule. The official, if you can see there in the center, 1 joule is the same as 1 kilogram times meter squared per second squared. And if you do some of your calculations with kinetic energy or potential energy, then we can take kilograms meter squared divided by second squared and call that a joule. Some other units of energy that you may have talked about or you used before, a traditional energy is the calorie, but it's a non-SI unit. So basically we will be using joules. So as you can see, the conversion factor, there's 4.184 joules in 1 calorie. And just as a FYI, like if you're talking about the calories that you're eating in your sandwich, that is really considered a kilocalorie, and so it is 1,000 of the kind of calories that we're talking about. So a kilocalorie that you would eat, 1 calorie that you would eat is a kilocalorie, or the same as 4.184 kilojoules. So just to keep that in perspective, the calorie is really a capital C. All right, so let's talk about kinetic energy. What if a person is moving in a car? The person weighs 130 pounds, which is the same as 59 kilograms, and they're going 60 miles per hour, which in metric is 26.8 meters per second. So if we plug that into our equation, the kinetic energy equals 1/2 mv squared. Don't forget to square the velocity. And so we end up with, you can see the units work out there, kilograms mass meter squared per second squared, which is a joule. And so we that person has 2.12 times 10 to the fourth joules, or 21.2 kilojoules of energy just by moving in a car at 60 miles per hour. All right, the other type of energy is potential energy. And like I said, it depends on the position, such as height, in a field of force, such as gravity. And so the equation there, E potential equals mgh, where m is the mass, g is the gravitational field, if we're talking about that type of energy, and h is the height. Okay, so for example, if we have water coming down from a dam, and that water, let's say it's at the top of the dam, and so if we know the mass of that water, and we know how high it is, and we know the gravitational field, we can figure out how much energy it has. The gravitational is well, it can change, but on Earth the constant is 9.8 meters per second squared. Oh, and the height is usually a reference compared to sea level. Okay, so let's look at an example here. Let's say a woman has woman and her bike together weigh 250 pounds, and which is 113.4 kilograms, and she is at the top of a 150-foot high hill. 45.72 meters. How much potential energy does that woman have by virtue of her elevation? Okay, so it's mass, 113.4 kilograms, times the gravitational field, 9.8 meters per second squared, times her height on the hill, 45.72 meters. If you multiply that through, you can see we get 5.08 times 10 to the fourth kilogram meter square per second square, which is the same as joules, or 50.8 kilojoules. Notice that what happens when that woman starts coming down the hill? Well, the potential energy will decrease, but it doesn't just disappear. It has to go into something else. So obviously it's going to go into other types of energies. It could be converted, of course, into kinetic energy because she's moving, and also some other kind of energy, frictional energy, heat energy, etc. So just as conversion, heat can neither be energy can neither be created nor destroyed. Okay, so what about that last bit of energy? Internal energy, we know, is the energy of the particles making up the substance of the chemical. And since we'll be talking mostly about chemical equations. So you can see here, total energy of a system is equal to its kinetic energy plus its potential energy plus its internal energy. All right, so what if we had water flowing over a dam? It has its potential energy because it's high up on the top of the dam. It has kinetic energy because the water is moving, it's just moving all over the place, spilling over the dam and just waves and things like that. And it has its internal energy, which is basically due to chemical interactions. Okay, so the first law of thermodynamics, of course, thermodynamics being the study of these energy changes, basically is a version of the first law of conservation. And so the first law of thermodynamics relates the internal energy to transfers of energy in or out of a system. Now, the two main kinds of energy transfers that we're going to be talking about are work and heat. So let's first take a look at what do we mean by work and what do we mean by heat. The first thing we have to do is make some definitions. So what are we talking about? Well, in a chemical reaction, we talk about system and surroundings. So the system is what we're talking about, the chemical reaction. It could, in this case, if you're looking at this picture, the system is the solution of barium hydroxide and ammonium nitrate. So the thing that is under study is called the system. And then the surroundings are pretty much everything else. It's actually everything else in the world, but clearly we mean everything else in the vicinity of the system. So the surroundings could be the glass container, the air's just surrounding the container. Okay, what is work? Work is an energy transfer into or out of a thermodynamic system where it affects the surroundings in an equivalent way of moving an object through a field of force. So what do I mean by that? So by now you might have already done a lab where we put some zinc in hydrochloric acid and we let it react and we saw bubbles, which means that a gas is being released. So we did it in the laboratory and the gas just gets released into the atmosphere. But what if we had a piston, some kind of lid on the system? So if you just let the system go and gas is produced, you can see that what will happen over time, because the pressure of the gas builds up, that whole lid will rise, or the piston will rise. So that is a type of work. You can see in this picture that also, we're not talking about heat right now, but in that reaction, heat is evolved, but also work is evolved because that lid has lifted. Well, what if we if we take that piston and connect it to something else, connect the piston to a wheel, to a cord, to a pulley, we can do work on the surroundings. The picture on top, as the piston moves outward, the cord pulls the weight upward. In this case, work is done by the system on the surroundings, and work is considered negative because it's going out of the system. And then if you look at the second picture on the bottom, if you tie a weight to that handle and let it go, it's going to pull the handle down, push the lid down, and in this case, work is being done by the surroundings on the system, and so work is being added to the system, and work is positive. Okay, heat is the other part of this. Heat is defined as the energy that flows into or out of a system because of a difference in temperature between the system and its surroundings. Okay, in general, and you probably know this very well, heat flows from a region of high temperature to one of low temperature. And then once the temperatures become equal, the heat flow stops. If you've ever touched a hot stove, you know exactly what I'm talking about. The heat flows to establish a temperature equality, and so there has to be a way of making those temperatures equal. Okay, just notice the bottom. Heat and temperature are sometimes confused. Heat is not the same as temperature. Temperature is a measure of heat. Absolute temperature, when you're talking about the Kelvin scale, is the absolute temperature is directly related to average kinetic energy. And so if you do heat up a gas, you increase the average energy and therefore you increase the temperature. But again, temperature is really just a measure of the kinetic energy, which is caused by heat changes. Okay, heat is given the symbol Q. Q is positive if heat is absorbed by the system, and Q is negative if heat is given off by the system. And then the heat of the reaction is the value of Q absorbed or evolved from the reaction. Okay, so if heat is absorbed by the reaction, heat going in, then this is considered an endothermic process. Q is positive, and if heat is evolved from the system into the surroundings, Q is negative, and this would be an exothermic process. Okay, so this is just another picture of what we saw. So exothermic means heat is going out of the system into the surroundings, and endothermic, heat is going into the system from the surroundings. And notice the sign Q is less than 0 if it's in exo, and Q is greater than 0 if it's endo. All right, so what do I mean by transfer of heat? Consider a vessel where T1 is greater than T2. So this is my very rude drawing of maybe like your coffee cup or something. So your coffee cup is hotter than the air around it. Well, what's actually happening inside is that, of course, inside the vessel, the molecules are moving faster because they're at a higher temperature. So as they hit with the vessel wall, they collide, they're going to lose some of their energy. They're gonna slow down. Generally, how that happens is it's transferred to the molecules on the outside of the wall. So as they slam into the wall, some of that energy can transfer to the molecules outside the wall. They start moving faster. And so eventually all the molecules inside and outside will have the same average speed, and so they'll be at the same temperature. And so you can think about your coffee cup as it sits there. It cools off if you don't drink it because the system temperature is lower than the coffee. All right, so this is something that that you will do in lab if you haven't already. Consider a system, so we're talking a chemical system where a reaction takes place. If you're taking the temperature of this system and the temperature falls, what that means is that heat is flowing from the surroundings into the system, and that's an endothermic process. And so usually what happens is the flask itself feels cooler because the system has absorbed the heat into the reaction, and it's taken it from the surroundings, and so the flask feels cooler. If the temperature of your system rises, the heat means it's flowing out of the system into the surroundings. The Q is negative, which is an exothermic reaction, and your flask will feel warmer to the touch because heat is released. Again, remember we're talking about a chemical reaction taking place. Okay, so let's look again at the first law of thermodynamics. So we can restate it by saying that the change in internal energy of a system is equal to the heat exchange, the amount of heat that goes into or out of the system, plus the amount of work that goes into or out of a system. Of course, the signs of Q and W can be different, so delta U could be positive or negative. It's just that we take whatever heat's gone into or out of, and we add whatever work has gone into and out of. So if you look at this picture, the system, let's say you have some gas inside a piston with a lid with a weight, and so the lid's free to move, and then you start to add heat to the gas. What's going to happen? The gas molecules will move faster, and so the volume will expand because it's allowed to. The weight has been moved, and so in this system, heat will be going in, and so it's positive, and the piston does work. The work is from the system to the surroundings, and so W will be negative. Okay, so in general, a reaction system can involve work as well as heat, but it depends on the conditions on which the reaction occur. So let's think about when do we usually run a reaction in the lab? We're usually, not always, but in standard reactions, we're in an open vessel, which means we're at a constant pressure, the pressure of the atmosphere. We can denote the heat of this reaction as Q sub P, heat at constant pressure. Also, at constant pressure, the only work that's going to be allowed is pressure volume work that we've been talking about, where the volume All right, so we're actually going to talk about a new property. It's fairly easy to measure heat, but not so easy to measure work. And so we're going to look at a new property called enthalpy, which is given the symbol H. It's an extensive property that is used just to get the heat of a reaction, the heat absorbed or evolved in a reaction. Okay, so first of all, what does extensive mean? An extensive property is one that depends on the quantity or substance. So that makes sense. If you react a very small amount, you get a small amount of heat out. If you react a whole bunch of your reactants, you're going to get a lot of heat off. So it depends on the amount. Enthalpy is considered a state function. So what does that mean? A state function is just a property where it depends only on its present state and is independent of any previous history of the system. So the way I like to explain a state function is another state function is altitude. And so let's say you're trying to get to, or let's say you're standing at the top of a mountain. The fact that you're at, say, 1,000 feet high has, or I guess you would, if you're at the top of a mountain, it wouldn't be 1,000 feet high, but okay, let's say 3,000 feet high. So if you're at the top of the mountain and you're at 3,000 feet, does it matter if you hiked straight up the mountain or if you hiked around the mountain and spiraled it around and around and around and around, or if a helicopter dropped you off at the top of the mountain? It doesn't matter how you got there, you are at 3,000 feet. So the same thing about enthalpy is that it just is what it is. It doesn't matter how it got there or where it's going. It's just what it is at that moment. Okay, so we can talk about the change in enthalpy. The change in enthalpy is generally, so delta H is always, of course, for anything where you're trying to find the change, it's always the enthalpy of the final situation minus the enthalpy of the initial situation. Or, since we're talking about chemical reactions, it's going to be the H of the products minus the H of the reactants. So delta H is very hard to measure individual H's, but delta H is a little bit easy because you can look at the differences between things. Okay, so we're going to define enthalpy as the change in internal energy, delta U, plus pressure, any pressure times volume work that we have done. So this is how we're going to define enthalpy. And then just looking further, since we know that delta U is equal to Q plus W, the internal energy is equal to the heat plus the work. And since we're talking specifically at constant pressure, that means we have Q sub P and work is minus P delta V, so it's only the PV work. And now if we plug that Q sub P minus P delta V into our equation up above, you can see that the P delta V's cancel out, and so delta H is defined as the heat of a reaction at constant pressure. So this represents the entire change in internal energy minus any expansion work, and it's, let's go to the next slide. Delta H is really just the heat absorbed by a reaction or released by an reaction in an open vessel, and we don't have to measure the work portion of delta U. And so it's pretty easy to measure delta H or calculate it, and so delta H is much more useful than delta U. And so for the rest of the chapter, we're going to talk about delta H, which is the heat energy of reaction when a reaction is open to constant pressure. All right, so now let's stick delta H into an equation. How is it related to a chemical equation? Well, usually you'll see it written as you have it right here. So here you have the reaction N2 plus 3H2 gives us NH3, and then it tells us delta H is negative 91.8 kilojoules. So the thermochemical equation is the chemical equation, including phase labels, and then the delta H is written directly afterwards. And What does a negative delta H mean? Well, that means that the products are lower energy than the reactant, so that's an exothermic reaction. Heat has been given off. It's important now we've just added another layer to our stoichiometry. So before we were able to do our mole to mole ratio. We know 1 mole of nitrogen reacts with 3 moles of hydrogen to give us 2 moles of NH3, and now we can add a new layer to it. So now we can say if 1 mole of nitrogen reacts with 3 moles of hydrogen, we're going to get 2 moles of NH3 and 91.8 kilojoules of heat will be released. So now it's kind of part of the complete equation. If we change the equation in some way, then delta H will also change. We're going to be doing this in a little while. And so keep in mind these important rules. Well, what if we write the, okay, so first of all, enthalpy is extensive, and so it depends on the amount of reactants. So if we rewrite a thermochemical equation and we multiply it, say we double it by any factor, or we double all the way across, then we also have to double delta H, because delta H is dependent on the amount. You're wondering, why would I double the equation? Well, we'll see in a little while. We're going to be using this procedure, but just keep in mind that if you double how much you react, then your delta H will double. Okay, another one to keep in mind is that enthalpy depends on the direction of the reaction. So the reaction we just looked at is exothermic, but what if we wrote the reverse reaction? If we write the reverse reaction, then of course it would be endothermic. And so the only thing that happens is delta H changes sign. And so if a reaction is exothermic, the reverse reaction is endothermic. So it's the same exact number, just a different sign, positive or negative. And then finally, be really careful. Enthalpy changes will depend on the state of the reactants and products. And so when you're doing some of these problems, note the phase label. So if you see below, we have 2H2 plus O2 giving us 2H2O. Well, if it's in the gaseous form, the delta H is negative 483.7 kilojoules. But if you're creating water in the liquid phase, which means we're also, so not only are we creating water, we're condensing it, it actually gives off some more heat, so negative 571. So just be careful at looking at the labels. Oh, there we go, circle those two. All right, let's just think about a couple of reactions that we know and tell me, what is the sign of the enthalpy change, delta H? If ice cube melts, is that endothermic or exothermic? Okay, so if you think about it, ice cube melting, what do we have to do? We have to put heat into the system. So the ice will absorb the heat from the surroundings, and Q is positive. So that means delta H is positive. It's an endothermic reaction. All right, what about taking a gram of butane and burning it to give us carbon dioxide and water? So if you light your butane lighter, the combustion will give us CO2 and water. Well, clearly that is giving off heat, which is the whole reason why we burn it. And so delta H is negative, and that's an exothermic reaction. All right, so how can we apply stoichiometry to the heats of reaction? Well, like I said just a little while ago, it just adds a new layer. So now if we have a balanced chemical equation, we know that the mole-to-mole ratios, we can equate different reactants and products to each other. And now when we know the heat of the reaction, we can add that to it as well. So if we look at this example, 2H2 plus O2 gives us 2H2O liquid, and the delta H is negative 571.7 kilograms. I'm sorry, 0.7 kilojoules. So what do we know? We know that 2 moles of hydrogen react with 1 mole of oxygen to give us 2 moles of liquid water, and it will also give off 571.7 kilojoules of heat. So we can relate any of these two things. We can say 2 moles of hydrogen is equivalent to negative 571.7 kilojoules. 2 moles of hydrogen is equivalent to 1 mole of O2. 1 mole of O2 is equivalent to negative 571.7 kilojoules. Negative 571.7 kilojoules is equivalent to 2 moles of H2O. So any of these can become part of the equation. All right, so let's look at this problem. Given the following equation, how much heat could be obtained by the combustion of 5 grams of hydrogen? Again, don't forget that if it's in grams, you need to convert it to moles. So if we just think out this problem, if we convert 5 grams to moles, then we know that for every 2 moles of hydrogen, we get off 571.7 kilojoules. Okay, so the first thing we do, you can see, is we convert 5 grams of hydrogen to moles. So we divide by 2.02 grams per mole. And so that'll give us right around 2.5 moles. And then if we multiply, we know that that we're going to be given off 571.7 kilojoules for every 2 moles of hydrogen. So multiply by 571.7 negative and divide by 2 moles because it's a 2-to-1 ratio. And so 5 grams of hydrogen will give off 711 kilojoules, or negative 711 kilojoules of heat.